So I'm going to be presenting some SAMI science. I shortened the title of my talk from the abstract a little bit to heavy metals in galaxies. I'm going to be talking about heavy metals, and by that I just mean anything heavier than hydrogen and helium and how they're built in galaxies. In particular, I'm really interested in how stellar metallicity estimates compare to gas metallicity estimates in galaxies. So I'm going to be talking a bit about that. First of all, though, the metal cycle in galaxies. So back when you form your galaxy, back in the good old days, 10, 14 gigayears ago, your galaxy is usually formed out of fairly pristine gas. And by pristine, I just mean mostly hydrogen. Okay. So the first generation of stars that are created from this pristine gas are very, very metal poor. Okay. But stars are really metal fusing machines. So they fuse these lighter elements into heavier elements. And this is how we get the heavy metals within galaxies. When stars die, some of them go supernova. And when they do that, they eject this heavier metals back into the interstellar medium. Okay. So, closing this cycle, we now have enriched ISM, and the next generation of stars takes up the enriched ISM and are more metal rich, and then they go on and fuse more and more heavy metals, and you can go round and around and around. And this is how metals build up within galaxies. So the scenario I just described is what we'd call a closed box model of metal enrichment. So that's assuming that your galaxy exists in a closed box with no external influence on it at all. And it just keeps sitting there fusing and fusing and fusing, getting more and more metal rich with time. So in reality, we don't actually think this is what we see in observations at redshift 0. Instead, we think there's a bit of a complex interplay between inflows and outflows acting on a galaxy. So on one hand, you might have inflows of pristine gas, or at least very more metal poor gas, onto your galaxy from, say, the cosmic web. That's going to act to dilute your ISM within your galaxy and make it more metal poor. Also, you can have outflows. So through either supernova or other galactic winds, metal-rich gas is ejected out of your galaxy. And if the gravitational potential of the galaxy is low enough, some of that metal-rich gas will escape. Otherwise, it will just rain back down as a galactic fountain. The point I'm trying to make is that it's a fairly complex process that's going on, and it's not fully understood by us. So the question that I wanted to ask is, what can we learn about the galactic metal cycle of SAMI galaxies? Okay. So to do that, we need to define some metallicities and measure them. So like I said earlier, I want to measure both the metallicities of the stars, stellar metallicities, and also the metallicity of the ionized gas in the ISM. We do this in two different ways. This is kind of important. For stars, we measure the ion abundance within the stellar continuum, which we measure from absorption lines. We do this because metal is very common in stellar atmospheres. Sorry, iron is a very common element in stellar atmospheres, so easy to measure. So the stellar metallicities I'm going to term Z star. Over on the gas side, oxygen is the third most abundant element in the ISM after hydrogen and helium, so that's also very easy to measure for the ISM. We measure oxygen abundances from emission lines, and I'm going to call this Z gas. Okay, so we can't measure Z star and Z gas for all galaxies, unfortunately. Over here on the left, I've got a star forming main sequence plot, so it's just the star formation rate as a function of stellar mass for all SAMI galaxies. Now, the galaxies that are colored green, we have reliable stellar metallicity estimates for. The galaxies that are orange, we have reliable gas metallicity estimates for, and the purple galaxies, we have both. Now, the seasoned star forming main sequence plot viewers among you might notice that the purple points really follow these main sequence lines. It's curved or straight, you can pick your favorite. We lose a lot of stellar metallicity estimates low mass, because we have low continuum signal to noise there, and we lose a lot of gas metallicity estimates in the passive region of this plot because there's no emission lines in these passive galaxies. So the following work I'm going to be presenting is really valid for star-forming galaxies on the star-forming main sequence. So we measured the gas and the stellar metallicities within a 1RE aperture. Now we want to compare the two somehow. So I've defined what I'm going to call the metallicity ratio, or delta G comma star. It just rolls off the tongue. But what it is just the logarithmic difference between the Z gas, so your gas metallicity, and your stellar metallicity. And I'm interested in how this changes with different galaxy properties. But this ratio, if your gas metallicity is very similar to your stellar metallicity, this ratio is going to be a low number down here. If instead your gas metallicity, if your gas is much more metal rich than your stars, you're going to be up here with a higher value. Okay. So yes, I'm interested in how this ratio varies different stellar properties. One of the things I'm going to look at is the stellar populations within the SAMI galaxies. So because I measured my stellar metallicities using a full spectral fitting code, what I get out for free is the weights of the various templates of stars used to fit this galaxy. So I split my stellar populations for each galaxy into two H bins. So old stars, greater than 7 gigayear, and young stars, less than 1 gigayear. And I've plotted the average metallicity of these two populations for each galaxy on this plot here. So this is just a one-to-one line here. If one of the hex bins lies along this point, that means that the old stars and the young stars are the same metallicity. Okay. So there's two regions of this plot I want to have a look at. The first one is up here, this red circle region. So these are galaxies that have metal-rich old stars and metal-rich young stars. Okay. Now the color of these hex bins is blue, which means that the gas metallicity is also very similar to the stellar metallicity. Okay, which is what I've said here. Now this blue circle down here is looking at galaxies who have metal-rich young stars but metal-poor old stars. And the colors of these hex bins are green and yellow, which means that the gas is much more metal-rich than the stars within these galaxies. So we can start trying to think about a scenario in which we can see this sort of behavior happening. The other thing I wanted to say is that it seems that it's the old stars that seem to be responsible for the differences between Z gas and Z star. So the young stars are pretty much always metal rich, but the old stars can be metal poor or metal rich, and that seems to depend a lot on this metallicity ratio that I've defined here. So here's two little cartoons about what I kind of think might be going on here. So the first one at the top is your stellar metallicity as a function of time. So you can think of this as your chemical enrichment history. The plot on the bottom is your star formation rate as a function of time. So a plot of star formation history. So going back to these two regions, so these galaxies in this red circle here, the ones that have metal-rich old and young stellar populations would follow, or might follow, a chemical enrichment history such as this red line here. So this is a very rapid enrichment at early times. The reason I say this is because if you take the average of the metallicity of the old stellar populations and compare it to the young stellar populations, they're going to be similar. Okay. Down for this blue circle down here, these galaxies that have metal-rich young stellar populations, metal-poor old stellar populations, you might have more of a slower, sustained metallicity, metal enrichment history, such that the average metallicity of the old stellar populations is metal-poor, but the young stellar populations is metal-rich. Okay, so the star formation histories that would give you these chemical enrichment histories are shown down the bottom. So for the red line, the galaxies that enrich early, you need a really early big burst of star formation. So a big peak, something like this, and then maybe you can peter off. Whereas for these blue galaxies here that enrich more slowly, you could have a more slower sustained star formation history across cosmic time. Okay, so everything is tied up in a nice little bow, right? Your gas to stellar metallicity ratio just depends on the star formation history and the chemical enrichment history of your galaxy. Easy, right? I almost want to end there, but I've got one more slide. The question is, can we actually compare metallicities, so stellar and gas metallicities, if they're derived from different elements, different London spaces? The answer is probably not. And I feel like I'm opening a little bit of a can of worms here. But our gas metallicities are measured from oxygen abundances, like I said earlier. Oxygen is an alpha element. And alpha elements are produced in type 2 supernovae. And these are on very, very short time scales, about 10 million years. Our stellar metallicities are measured from iron peak elements, and iron peak or iron elements are produced in type 1a supernova. And the time scale for these are much, much longer. So the problem with this is, depending on the star formation history of your galaxy, depends on your oxygen to iron ratio that you're going to be observing. So galaxies that have, big bursts of star formation early are going to show a bit of your knee in your O and Fe ratio at later times than galaxies that have more sustained star formation histories. We can show this in the SAMI galaxies by this plot. So at fixed stellar metallicity, your metallicity ratio depends on the specific star formation rate of your galaxy. And specific star formation rate is a good proxy for the star formation history of your galaxy. So the point I want to make is that the gas and stellar metallicities can't be compared between galaxies of differing chemical enrichment or star formation histories. Okay. So did I just invalidate all of the work that I'm presenting? Well, no, but I've run out of time to say why. But what I will say in conclusion is just that we can and should use stellar and gas phase metallicity indicators in tandem to fully constrain our chemical evolution histories of galaxies. The ratio of the two depends on the chemical enrichment and the star formation history of the galaxy. And if you're interested in how I attempted to get the stellar and the gas phase metallicities onto the same abundance scale, I have paper draft, which is going back to the co-authors this week and will hopefully get submitted quite soon. And I'm very, very happy to share that with anyone in Astro 3D if you're interested. So I will leave it there and I'm very happy to take questions. Thank you.
Thank you so much, Amelia. Awesome. We have a question from Anshu, who is asking, how do you explain galaxies with metal-rich old stars, but relatively metal-poor young stars? Basically on the top left of the plot that you showed 2 slides earlier.
Ooh.
Yeah, that one.
Say again,
metal-rich old stars, but relatively metal-poor young stars. How do you explain that?
Right, so I guess I would kind of say that that's sort of this white region where there are no galaxies. I would hope, because I guess I can't really explain it at you. I'd be interested if you could, but I think, I mean, there's a couple of galaxies which, you know, might just be scatter and fit problems and things like that. I don't have a good answer for you, I'm afraid.
Yeah, thank you so much. Okay, one more question from Julia. Matthew and Carl, could you maybe ask the questions in the Slack channel? Thank you. So Julia was wondering, have you had a look at the stellar and age metallicities at more than one effective radius? Are they different? Are there any differences, and would you expect something to be different?
Yeah, so that's a really good question. I haven't, no. A couple of reasons. You would probably run into issues with signal to noise out there for your stellar metallicities with SAMI, but it would be very interesting to do. I can't tell you off the top of my head what I think I would find, so I'll have to have a think about it. And
no worries. I mean, the good thing is, yeah, the question is on the Slack, so don't worry.
Okay, good.
Yeah.